I'm going to do T1 like this, and then I'm going to talk about the fact that it says correct to 0.1. Hopefully this is ringing a bell in your brain of correct to this many decimal places. That sounds like bounds that we already learned about. If it's correct to this, they're giving us a level of precision. So what we're going to do here is we're going to say that P is 0.1. The first thing we need to do when we know what P is, we need to figure out what is P over 2. Well, P over 2 is 0.05. You can plug it into your calculator. Just because I'm doing it in my head does not mean you have to do it in yours, which means then I'm going to create my bound for T1. So 11.5 is going to be between 11.55 and 11.45. Again, you're adding and subtracting this 0.05. So that is already a piece of information. So I don't even know what I'm doing. Right? At this point, I just know I've been given information that I know what to do with. And so I'm just going to like go down that rabbit hole for a little bit and then continue on reading. So it says, while the second timer measures the time T2 to be 11.50, correct to 0.01. So in other words, one of them is correct to 2 decimal places and one of them is correct to 1 decimal place. While they're giving us both the same measurement, there's 2 different levels of precision. I wrote down my P. I wrote down my P divided by 2. I'm going to go ahead and write in my bounds. 11.50 lives between 11.505 and 11.495. I had to think about this as 500 in order to add and subtract that 5, or just use your calculator. That's totally fine. Okay, so we've got our bounds situated. It says find the magnitude of the maximum error in each of the measurements and compare their size. So first of all, we're talking about finding the error here. In this error, we're trying to find the percent error, but not just any percent error, the maximum that our percent error could be. Well, the reason why there might be an error is because our rounding has created some sort of error here. So we want to realize that the magnitude of error is how far off did this rounding make us go? How far off did rounding make us go? And the fact that we're talking about a maximum error means that we are going to try the extremes. We are going to test the extremes. The extremes of this case means the very edges of our bounds. So we've got some edges of our bounds. We've rounded here. This is the approximate value in the middle here. And the very edges of our bounds means that from here all the way over to here of our bounds could be where our exact value is. So our exact value, the extreme of our exact value could be just below 11.55. We could do 11.54999999, which is essentially 11.55, and talk about how that is the extreme of our bound. So when it says find the magnitude of the maximum error in each of the measurements and compare their sizes, we need to take each maximum error and compare it here and find the percent error. So if we're talking about our maximum value here, our error on T1 using our maximum value. Let's start with planning, right? We need to write down what our approximate value is. Our approximate value is what we rounded to, right? So what we rounded to is 11.5. Which means that our exact value, and it's the extreme of our exact value, is going to be here if we're talking about the maximum. So 11.55. So we're going to plug that into our percent error formula and then calculate it out. So our error is approximate all the way up here, approximate minus exact, all over exact. We're going to take that absolute value and multiply by 100. This one is going to give us a negative value when you do this decimal. Absolute value will make it positive. You don't have to then do the absolute value in your calculator. You could just multiply this by 100 and then just say, oh, well, instead of it being negative, it's just going to be positive. The number that you get here is going to be 0.43%, which means after you're done multiplying by 100, you still get 0.43. So that's going to be our error on the maximum of the T1 bound. Our error on the minimum of the T1 bound is going to be still the same approximate. We've still rounded to 11.5, but our exact then is going to be the extreme in the other way, which is 11.45. Again, remembering that we've rounded to this number. These bounds are the neighborhood or the beginning and end of where our exact value is. It's somewhere within this range. We just don't know where. These are the extremes of where the exact value could be. So we're using the extremes to test the maximum error that could occur. So plugging all of this in to find that error, we're going to do approximate. Minus exact all over exact, multiply it by 100, and we will get 0.44%. So for some reason, the percentage here is slightly more than the percentage there, which is why we're testing all of them. And we've only tested T1. We now need to do the same for T2. So our maximum error for this guy is going to be, our approximate now is going to be 11.50. Now 11.50 is only helpful here when we're talking about the bounds, because we knew it had to be 505 as opposed to 55. Really 11.50 is 11.5, so it's pretty much the same as what's over here. Our exact for the maximum up here is going to be 11.505. Plugging it into our percent error formula. It will give us, after multiplying by 100, it will give us 0.0434, and that is a percent. A very, very tiny percent. All right, now we're going to do our last extreme of these bounds, which is this number right here. So that's our minimum, our error on the minimum of T2. Our approximate value is still 11.50. Our exact now is 11.495. To calculate the error, approximate minus exact, all over exact, absolute value times 100 equals, and we get 0.0435%. Okay. So we have calculated the percent error on the maximum error that could occur. The magnitude is the size, or in other words, the number of the maximum error that could occur with these bounds. And then it says to compare their sizes. Well, notice that with T2, the sizes are significantly smaller. So an answer here is T2 percent error is significantly smaller, which makes sense if you think about it. If you are rounding to a smaller decimal, in other words, if you are becoming more and more precise with your rounding measurements, your percent error, your range of error that you could possibly have from rounding is going to get significantly smaller as well. So that's pretty much the general gist, is that the more decimal places you round to, the smaller by magnitudes of 10, meaning I divided this guy by 10 in order to get this one. So by magnitudes of 10 means I either multiplied or divided by 10. So by magnitudes of 10, this guy is a significantly smaller percent error, which is really good. Okay, so that's the general idea of percent error. You have a formula. You plug in with the formula, remember what your approximate is versus your exact. The number one issue that I see from most students, the number one mistake that I see from most students is that you accidentally put approximate on the bottom instead of exact. So just make sure you're always dividing by exact. This subtraction doesn't matter which one is first because you're taking the absolute value. So if that makes sense to you, that it doesn't matter which one is first in the subtraction, awesome. If it doesn't, then just follow the formula because it's in your formula packet. And you can use your formula packet all the time.